And well, we're doing one kind of little new thing. We're going to adding one thing to the model that we've been doing. All right. And can someone close the doors so we don't bother people in the library? Okay. And for people online, I'm assuming the way I have this set up, when I look at the video, it looks like you should be able to see everything clearly, but you have to let me know if I'm doing something in a way that makes it hard for you to learn online. And even though I did hand out a new sheet, we're not going to start on that today. I don't want to start on something new. I believe the last thing we did was number 9 on the worksheet. Does anybody think we did? Okay. Okay, so we're going to start off number 10 on the worksheets. Number 10. And so here we're just basically reviewing what we did before. So here I'm giving you a scenario where I'm telling you that D is 20,000. That's the total. Let me keep with the example that we're talking about. We're managing inventories of chicle base to make sure we always have enough, but not too much of our chicle base for our production of natural chewing gum. And so D 20,000 means that we need 20,000 per year. Little c is 0.05, means that chicle base costs like 0.05 per pound. R is 500, which means it costs us $500 every time we place an order. And H is 5, which means to store 1 pound of chicle base for 1 year in our warehouse costs us $5. And then ask, what is Q star? The number units we order at each order. What is N star? The number of orders per year. And what is T star? The length of time between orders. And we've already derived this stuff at least twice, and so I'm just going to go straight to the equations. I think this is the first time we've actually plugged numbers in to get an optimal Q star. So we used calculus to derive the fact that the optimal order quantity is 2 times R times D divided by H raised to the 1/2, or the square root of all that. And so now we can just plug this stuff in. We say R is 500. And this is a 5, I'll try to write better. And D is 20,000. And then H is 5. And even though I have done these in advance, I'm going to always do the calculations again myself to make sure I don't go too fast with stuff. And so you can do the calculations if you want as well. And I get 2,000. And remember, this is units per order. So this means every time we place an order, we're ordering 2,000 units. It doesn't matter what time of year it is or anything like that, because remember, one assumption of the model is that we need the same amount of chicle base every day, every single day. This assumption we can easily change later, but we're starting off simple. And then for T star, we said that T star, the length of time, the amount of time that has to pass before a new order is placed, where time is expressed in fractions of a year. One way we said that, it was Q star divided by D, and we spent a good bit of time talking about why it's like that, but then we also derived an equation that said T star is also the square root of 2R divided by HD. So this is one of those things where we have two expressions. They're the same thing. Remember, if you just plug in the optimal Q star in here and simplify, you get this. You have two different ways you can calculate T star, and so you've got two ways of calculating to make sure. If you get them right the both times, then you're probably doing things correctly. Let's see, where am I? And so if we do it the first way, we said Q star was 2,000 per order, and we need 20,000 per year. The other way of calculating it was the square root of 2 times R, which was 500, all divided by H times D. H was 5. D was 20,000. And this is supposed to be. So this entire expression is under the radical. And so if we do both of these, well, it should be 0.1, obviously. You can look at this and tell it's 0.1. But then I'll do this one on the calculator too to make sure I get the same thing. And 0.1. Now, what does this mean? 0.1 or 10% of a year passes between orders. So if we want to know the days for that, 0.1 of a year, there's 365.25 days in a year. So about 37 days passes between orders. So if we place an order today, we're going to need a second order after about 37 days, the third order after about another 37 days, and so on. And then last thing it calls for is N star, number of orders per year. And we said the optimal number of orders per year, it can be calculated as 1 D divided by Q star. Remember, multiple times we described how D divided by Q is the number of orders per year. If Q star is the optimal order size, then D divided by Q is the optimal number of orders. And we also said that T star was Q divided by D, and so thus N star is also 1 divided by T star. So if we're placing a new order every time 10% of a year goes by, then logically we're doing 10 orders per year. Now we're going to number 11 of the same worksheet. Here's where we make one change to our model. And you may not have noticed this, but this handout I gave you, that's one figure from chapter 9 that's posted as a reading. On the back of that, there's another figure, and that's where we're going to now. See, what we're doing now is our economic order model, the way we did it, we said that there is no lead time, meaning the moment you place a new order, it instantaneously arrives. So when we placed an order at this time period, it's going to be received at the exact same time period. But now what we're going to do is we're going to have a lead time, meaning it takes a certain number of days for it to arrive at our factory. And so, maybe now, instead of an arrow here, there's an arrow a little to the right, because even though we're placing the order here, it takes a little time for the order to arrive. And the only thing this is going to change about our model is when we place the order. It's not going to change the optimal order size, not going to change Q, it's not going to change T, it's not going to change any of that. The only thing that matters is when we place the order. Okay. And one way to think about that is this. Okay. And again, this is a figure from your text, from the chapter 9 of the readings. Remember that the way the inventories work is that we order Q star. Time goes by, we draw down the same amount every day. When T star time goes by, we're completely out of our chicle base and we need to order more. So at T star, we place a new order. We're ordering the exact same amount Q star. So inventory, this is inventory on hand. At T star, inventory goes from 0 to Q star. And then we immediately start drawing it down by the same amount. When 2 time periods have gone by, 2 times T, we're placing our second order. At that time period, we're completely out of inventory. We place another order, and it comes instantaneously. And again, the reason why in this model you wait until you're completely out before you reorder is because we were assuming no lead time. But of course, in reality, if you know you're going to be out in 2 days and it takes 2 days for it to get to you, you need to make that order 2 days in advance. That's all it is. And so all we need to do in our model is figure out how to adjust these things to figure out exactly when we reorder. And here's one way to think about it. Now, lead time can be expressed in days or in fractions of the year. If I ever give you a problem and I don't tell you which one, it should either be inferred for the problem or that means I didn't write a good question and you need to let me know. But let's just think about this for a minute. You place an order here, you get Q star. Every day you draw down the inventory about the exact same amount. So inventory goes down and down and down. And because we know exactly what demand is every single day, we know exactly when we're going to run out. And then suppose I tell you that we have a lead time of L. Well, here I'm expressing L in days divided by 365.25. So if L was 365.25 days, that means there's a whole year lead time, and you need to order like a year in advance. And so what we do is we say, okay, we're going to run out right here. And if lead time is L, we need to order L time periods in advance. So instead of ordering here, we just order here. We order at time T minus L. Simple as that. So if we're saying at what time period do we reorder, it's right here at time period T minus L. Often in software, inventory, well, almost always in software, inventory is not described in time units, it's described in units in inventory. So usually you have what's kind of like an inventory position where you say once we hit a certain amount of inventory, then we need to reorder. And so we need to be able to say, in addition to just knowing that we reorder at T minus L, we need to know how low do inventories need to get before we reorder. And it's going to turn out that once inventories reach the level of Q times L minus T, then that's the number, that's the amount of inventory at which you reorder. Yeah.
Does FIFO and LIFO ever play a role in any of this?
Does what?
FIFO and LIFO?
The first in, first out, last in. No, that's more of a
It's more accounting.
Yeah, that's what.
Yeah, we're talking inventories. That's what I asked.
Yeah, and I'm sure that there's in software now things are integrated. So the question was, there's a thing called FIFO, first in, first out, LIFO, last in, first out. It takes me about 1993. And there's an accounting thing. You always talk about with the inventory here. We're talking about inventory. So we're talking about supply chain management stuff. That's an accounting thing. We are keeping them separate just to keep some concepts separate. But in software, all the accountants are going to be using the same software for the most part, and supply chain managers are going to be using the same software. So those two are integrated now. And even if the people managing the warehouse, they may not know it's integrated with accounting, but the accounting people know. Yeah, a lot of the software now really integrates if you can convince a company that you've got this one big software that can handle everything, you know, you can charge a buttload for it because you've got some great software. Buttload is a metric term. That's the metric system. Okay. You know, there was buttload was an actual thing. It was like that's why we have a Boston butt. That's partly why, you know, the Boston butt comes from the shoulder, not the actual butt, but that's where it comes from. It used to be a real measurement. So I didn't say a naughty word, you did. All right. Now one way of thinking, so how do we know it's Q at L divided by T? I'm going to show it to you one way real quick, and then I'll show it to you more logically in another way. So suppose we know we've got this system where every time we order, we're ordering Q star amounts, and we know that we're going to run out at time T. And we know we need to reorder at time T minus L, and we need to know at what level is that. Well, notice we can just say this, okay? If we want to solve for this question mark, we know that it equals, we've got this equation here, this line, the intercept is Q star. It's linear. The slope of the line is just going to be negative Q divided by T, because think about rise over run. Like when you go from this point to this point, the rise, we go from Q star to 0, so the rise is negative Q, we lose Q. The run, we're going from here to there, so the run is T star. We want to solve for the point here, where on the x-axis is T minus L. And so if we just solve for this, I'm going to just ignore the stars for the time being. And of course, this is just Q minus Q, so the only thing you're left with is Q times L divided by T. So again, all we're doing here is the exact same model, but now we have a lead time, and instead of saying we need to reorder Q star at time T0, at time T, or instead of saying we need to reorder Q when inventory's down to 0, we say we need to reorder Q star at time T minus L, or equivocally, we order Q star when inventory reaches a level of Q star times L divided by T. And now we're just going to do 2 quick problems where we use those. We're going back to the worksheet. Let's see, we just did number 10 on the worksheet. Now we're doing number 11 and 12. And number 11 and 12 take number 10, and they're just adjusting it for lead time. So number 11 says, following from number 10, suppose lead time denoted L is 15 days. So there I'm telling you exactly that it is in day units. What is L expressed as fraction of a year, and at what point in time should we place a new order? So L equals 15 days or 15 divided by 365.25 So another way of saying L is 0.041 of a year, or 4.1% of a year. When I give you a question about this, you know, how you round can always make a difference in your answer. If I remember, I'm always going to tell you how many decimal places to round to. If I don't, you need to remind me, because I think the way you're going to put these answers is putting in an exact number. So our answer to number 11 is we order Q star units at time T star minus L. We already said T star was 0.1, 10%. L was 0.041. And if you look at that, your lead time, L is about half of T, right? So that means when you're halfway to running out of your inventory, you need to reorder. So that's going to mean when your inventory is down by about a half, you need to reorder. Well, let me actually just leave it like that. So it's at time 0.059. You reorder. If we express it in days by multiplying it by 365.25, that would tell you how many days we need to reorder. Okay, what I want to do, I want to map this. I know this may seem really simple, but I want to show it just another way to really get the intuition, show you don't actually need algebra to calculate this stuff. Let me just recreate this graph and show you what we're doing here regarding this part. I don't think you need to write this in your notes. So there's a time when we order Q star, and there's a time where we run out, and in this particular example, we run out at time point 1, 10% of a year. And then we know that the lead time there I'll make it more realistic. The lead time is 0.041, and so we need to reorder at 0.059. So this is like our reorder point here. But this is T minus L. This is L. Okay. And so this amount of time passes before you run out. But because we have a lead time, we know we need to reorder about right here. And the way these numbers are, you're running out at about halfway between the time you need to, between the time you run out. And so if you have to reorder about when you're halfway there to running out, then you've used up about half your inventory by then, right? Because you're using the same amount every day. So you know this number here is going to be about 1/2 Q, which is what 0.04 divided by T is. And so when we solve for that reorder point, what you said was Q L divided by T, which here is Q L about 0.04. And so there's some intuition of why that's a reorder point. So if you have L time left, and then that means that like L divided by T would be about the fraction of the inventory you should have left in when you reorder. And so now we can finally go and answer number 12. 12 is the same thing, but it's just saying that another way of determining when to place an order is an inventory threshold, where the new order is made when the inventory falls to a certain level. Given your answers, question 10, 11, at what value of inventory on hand should we place a new order? And so we say, this is number 12, reorder at where inventory on hand equals Q star L divided by T. Our Q there was 2,000. Our L was 0.041. T was 0.1. Yes, you're ordering Q units, 2,000 each time. When you get down to 820 units, that's when it's time to reorder. That's what that means. And that, everything we've done there, that is the economic order quantity model. That's what you need to know. So you need to know the math behind it, all those things we just did, some relationships between different things. But we're not going to discuss anything more about this particular model than we have now. We're going to do another practice question on it in a minute. But we are going to do one other model, but no more extensions to this model, really. So what we're going to do now, we're going to go back to exam 2 from 2019. And here I'm going to go through them a little faster, I think, but this is just practice. And again, these are the questions I'm going to be asking you on assignment, so it won't be anything real surprising. So now on to 2019 exam 2, and have we done number 11 on that?
You haven't done 8, 9, or 10.
Okay. We're going to go number 11. We've already discussed what lead time is. I'm not using the term pipeline inventory anymore, so you can scratch that out if you want. Number 9, you can scratch that out. Okay. All right, number 11 says, suppose you order 13,000 units at a time and the annual demand is 140,000 units. What is the... Tell you what, instead of that, let's skip to number 14. And then we'll get out early. There's only so much you can take of this stuff, I know. So we're going to number 14 here. This is where I'm giving you numbers for D, C, R, H, and L lead time. It's starting off with a 0 lead time there, but when you get towards the bottom, it's going to change the lead time. All right. So the first question it's going to ask there is, what is the optimal order quantity? And, we've done this a number of times before, but we know it's going to be Q star equals 2 times R times D divided by H. And so all we have to do is plug in the values. R is 10,000. D is 500,000. And H is 3. Did I press record? Oh, good. I was scared I didn't press record. Five, 7, 7, 3, 5. What does that refer to? What are the units there? Units per order. Every time we place an order, we'll order in 57,735. And of course, in reality, what you may just do is say 57,750, but and then the next question is, number 15, what is the optimal number of days between orders there, T star? And notice I am specifically asking for days there, so you'll first solve it for a fraction of a year and then convert it to days. But one quick way of doing this is 15. So we know the optimal time period between orders is just going to be Q star divided by D. Q star, we said, was 57,735. Big D, total needs over the entire year, 500,000. is about 11.5% of a year. So what that means is that we're going to run out of inventory in about 42 days. So if there's no lead time, that's when we have to place our new order. If there is a lead time, we have to say, let's order enough in advance so that the new Q star comes back after 42 days. How many orders will we place per year? We said that could be calculated as D divided by Q star, or 1 divided by T star. I'll just use the latter. 1 divided by should be a little under 10. About 8.66 orders per year. Okay, then it asks, now remember, we're starting off with this model where there is no lead time. And I don't have a positive lead time yet, but the next question says, you should order Q star units when inventory on hand equals what? There's no lead time here. It arrives the moment we place the order. So we wait till Q star, our inventory on hand equals what when we place a new order? 0. Yep. But then we modify it a bit and we say, suppose that instead of L equals 0, L equals 20 days, you should then order how much units when inventory on hand equals so-and-so. And so now we just come here and we say that L equals 20 days or 20 divided by 365.25. Or about 5.47% of a year. And so that means, to answer number 18, now that we have a lead time, does Q star change? Look at your equation for Q star. Do you see L in there anywhere? Nope. So the amount you order does not change with lead time. So we're still ordering the same amount, 557,735, when inventory on hand equals, let me go to another sheet for this. So we reorder Q star equals that amount. When inventory on hand equals Q star times L divided by T. Q star was 57,735. L was 0.0547. And then T was 0.11547. Units. So our answer number 18 was you should reorder Q star 57,735 when inventory on hand means the amount of stuff in your warehouse equals 27,350 units. Any questions? Steve, you think we should stop here, or you want to just jump into the other model? You want to stop here? Okay. Everybody okay with that? All right, let's stop here. Have a great weekend. I love you unconditionally. I'll see you Tuesday.